Everyone. All right, hi. Welcome back to Math 234, Multivariable Calculus. I'm your host, Steve Dragoo. Today, we're reviewing for exam number 2 in For Posterity. This is the fall semester of 2025. Just in case you happen to be watching this video at a time that isn't this semester, which happens. So, if you look over to the left, you can see in the navigation where I've got my review, or the review that we're going to do right now. So it's just in the normal live streams tab. It's just, right at the end of our exam 2 content. And the very first thing that we're going to look at is the formula sheet, right? That's this guy right here, I think. And in particular, I want to highlight the things that I think are going to be helpful on exam number 2. So if it were me taking this exam and looking through the formula sheet at stuff that I think jumps out at me for this section. We're doing a fair amount with planes. So I'll just highlight that we have that plane equation. It's got a normal vector A, B, C. Keep in mind that a lot of the times now we're using the gradient of some function to find a normal vector. In particular, if we're looking for a tangent plane, the gradient will get us that. So I think that is worth knowing about on this formula sheet. Vectors in space, everything in that section is still helpful. That was primarily exam number 1. So I won't focus too much on it. Same thing with arc length. We did build up out of arc length to do our line integrals, but I don't think we necessarily need that formula directly. There are a few trig identities through here, which I don't really think they'll be that necessary, but just in case you need one, here they are. The chain rule is on here. Definitely going to want that. So let's go highlight our chain rule. That'll come up. Hey, we have our everything in the more on surfaces, really. The directional derivative and the second derivative test. And off the second page of the formula sheet, a lot of this is stuff we don't need, but we do have fundamental theorem for line integrals. We just did that one. We won't need Green's theorem, though. That's way later. And I think these transformations are also going to be helpful. So those were our cylindrical coordinates, and these are our spherical coordinates. Worth pointing out that those are given to you, so you don't have to have them memorized for the exam. All right, and from the formula sheet, that's most of the stuff that I think you'll want to know about. That stuff just highlighted there. The rest of it, if you see 2 integral signs in a row, you can safely ignore that for now. We aren't doing double integrals yet. That's Friday, which is notably after the exam. So, with that said, let's actually start reviewing some of the material, starting with tangent planes and approximations. In particular, those were linearizations, which is really just a fancy tangent plane. The thing that we're going to be after, given I've got the function square root of x plus e to the, is that 8y? Yeah, it is. It's cut off on my other screen now. Given that we've got that. Oh, that's right. I'm just thinking of the wrong thing. Yeah, e to the 8y minus 3. I want to be at the point 30, and I'm after a linearization. Keeping in mind that a linearization and a tangent plane are really the same thing. So, what do we want? Well, a few things. I know that I want to evaluate the function at the point 30, but I also want both of the derivatives, both of the partial derivatives at that point. So the way I sort of think about these linearizations is that there is a center value, which is just the exact value of the function at the point that I want to center my linearization at. And then I've got an x slope and a y slope. Or at least that's what helps me organize my thoughts. Those aren't like technical math terms, which is why I'm going to throw them in quotes. So those are really just Steve terms. But again, I think it's helpful to kind of think about the way that the linearization is set up. It's centered somewhere and then has changes in x and changes in y. So we should probably take some derivatives and also plug some numbers in. How about we start with f of 3, 0? All right, just plug in the point to figure out my center. And that looks like something. I think it's the square root of 3 plus 1 minus 3 on the outside. All right, e to the 0 is going to be 1. So the square root of 4 is 2. And 2 minus 3 is negative 1. Yeah. Stop it. All right, then I'm going to need to start getting derivatives. And I'm scrolling away from my function, so I'm just going to rewrite it here. F of xy was the square root of x plus e to the 8y minus 3. Let's take you just slide a little bit over to the side. All right, because now I need an x partial and a y partial. So f partial x is going to be 1/2 times x plus e to the 8y to the negative 1/2, since that's the derivative of a square root function. And then the chain rule says multiply that thing by 1. Maybe if I rewrite that to look a little bit more clean, this will be just 1 over 2 times the square root of x plus e to the 8y. Of course, the derivative of that constant negative 3 is just 0. So now that I have my x partial, I should also plug my point in. So this is 1 over, well, I already know the square root of 3, 0 is going to be 2. We did that in the first calculation, so that looks like 1 over 2 times 2 to be 1 over 4. I'll go do the same thing for a y partial, f partial y. And similarly, 1 over 2, 1/2 times x plus e to the 8y or nope, not times yet. That's all to the negative 1/2 power. Multiply that by the derivative of the inside, which is e to the 8y. And then the derivative of 8y is 8. If I just do my chain rule enough times, I'll eventually get to an answer. So ultimately, I might call this thing 4e to the 8y divided by the square root of x plus e to the 8y. Then also need that y partial at 3, 0, which if I plug it all in, I'm going to get 4 in my numerator and 2 in my denominator, right? So that'll be 2, assuming I did all that math correct. Sure, someone will let me know if I missed. And then what do we have next? I think we just need to assemble all of our pieces. I think at this point we have all of the parts we want. So I'll just write down my linearization again, L of xy. It is some center value, which I think we said was going to be negative 1. Right, that was just the function value at the point. Plus the x bit, which will be 1 over 4 times x minus 3. Plus the y bit, our derivative was 2, and our center was at 0. So that's my whole linearization. Minus the part about actually plugging in a point. Cool. Okay. So now that we have our linearization, let's go figure out what we were trying to approximate. So just haven't written that part down yet. We're attempting to approximate f of 3.3 and 0.01. So I'll plug those in. L of 3.3. Well, let's try this one more time. F of 3.3, 0.01 is approximately the linearization at 3.3, 0.01. And the linearization is -1, -1 plus 1/4 times 0.3, 0.3 plus 2 times 0.01. And if this were my written exam where I don't have access to a calculator, I would stop right there. Just leave that as it is. We don't need to actually compute a value there. All of its constituent pieces are enough. I mean, I could multiply that all out, but why bother? Mhm. Okay. So after tangent planes, I think we moved into parameterizations, specifically parameterizations of surfaces. So I'm just gonna borrow a page out of the notes, but I think I'll also make some changes here since we've already done this exact problem before. If you're looking at this, there's a page number at the bottom. It's page 19. So it's in the parameterization of surfaces part of the notes if you want to go look at the original problem. But I want to, again, change some things just so that we can see some different numbers. I'm still going to look at the parameterization of a cone and a sphere, though. Just want to change some things. So let's instead work with the cone. It looks like this, the square root of x squared plus y squared over 3. Notice that over 3 is going to be on the inside of the square root. And, we should probably change the radius of the sphere too. How about 49? That way I don't have to change the 4. All right, and then we'll do it live. So, what are we trying to do here? The first example is going to see us parameterizing where did it go? Here it is. It's going to see us parameterizing the cone. Right, so notice then the first part says parameterize the cone that's going to be inside the sphere. So the cone is the thing that I should be parameterizing. That's the thing that I ultimately want to have the x, y, and z components describe. I'll worry about the sphere when I get to the bounds of this parameterization. But if I just want to parameterize a cone, it's helpful to think of that in cylindrical coordinates. Cones have very nice equations in cylindrical coordinates. So I'll write in the notes for the cone that I want to think about cylindrical coordinates. I think I wrote the exact same thing down in the notes. Think cylindrical. Right, the easiest example of a cone in cylindrical coordinates is just the equation z equals r. And in fact, that was the equation that we had when we were doing the original problem. So before I made these edits, this was just the cone z equals r. So in cylindrical coordinates, what do we have? X equals r cosine theta. Y equals r sine theta. And then let's kind of put z equals r in quotes here. But our specific cone isn't going to be that anymore. But we're expecting it to look something like that equation. In particular, I think z is going to look like c times r, where c is a constant number. all you gotta do is figure that out. So that's our next step, getting to that. If I'm going to use x is our cosine theta and y is our sine theta to go get z, wait, don't be like that. Z, which I know from the equation that I was given, this is going to be the square root of x squared plus y squared over root 3. So r squared cosine theta squared plus r squared sine theta squared all over 3. So I can just replace x and y with r cosine theta and r sine theta. So this ought to look like the square root of r squared times 1 all over 3, which in turn 1 over the square root of 3 times r. Since I'll just take the square root of r squared and get r. Aha, gotcha. So what I am doing there is taking this equation of the cone and yeah, bringing it right down here. Oh, and then plugging in for x and for y. Hi.
You just do x squared plus y equals r squared.
Couldn't you just do x squared plus y squared equals r squared? Yeah, you totally could. Instead of needing to substitute for the cosine squared plus sine squared bit. Yeah, that's totally fine as well. No. Yeah, I just wanted to show from as low down in the process as I could to show all my steps. But yeah, if you in fact wanted to jump straight to the equation of this cone is 1 over root 3 times r, or z equals 1 over root 3 times r, that would be fine too. Like we would understand that jump. That said, it's probably helpful for me to show you all of the steps that get you there. And then you can start skipping steps when you feel comfortable. Just don't make mistakes when you do that, because it hurts. So yeah. But at this point, we basically have our entire parameterization. It's just missing a couple of steps to kind of round things out the way that we usually see parameterizations. I'm just going to replace r and theta with s and t. The step isn't strictly necessary, but just to kind of match the work that I think we should have seen at this point, I'll just do that. So r of s and t is the parametric set of equations s cosine t s sine t. I come back here, sine t. And the thing that we got for z, which was 1 over root 3 times s. So you might think that at that point you're done, but not quite, sadly. Don't forget that all of our parameterizations for surfaces require bounds on our parameters. So we got to come over here and say that t is stuck inside of some stuff. T is in between 0 and 2 pi, since it is our stand-in for theta. And s is also in something. 0 to something. I'm gonna leave that blank for a second because we actually haven't figured out what our radius is going to be bounded by yet. So we should go figure that part out. That'll also help us when we get to parameterizing the sphere, which is going to be the second half. But okay, let's just go over here into the margins and write down the intersection of the sphere, intersection of the sphere and the cone. So I need to figure out where this S value should stop. It'll eventually hit the cone, or the cone, it's already on the cone. It'll eventually hit the top of that sphere, in which case I need to stop my parameterization because I want only the parts that are inside of this sphere. In order to do that, I want to just plug everything in to the equation of my sphere. So starting from there, x squared plus y squared plus z squared is equal to 49. Notice that this is the first part in the problem where I'm actually using the sphere itself. I got all of my parametric equations from the cone alone. The sphere is just going to tell me where to put my bounds. But at this point, I can just plug in everything I know for x, y, and z. Here I will use that substitution. X squared plus y squared is equal to s squared, or r squared if you were feeling fancy, plus z squared is going to be s squared divided by 3. S squared divided by 3. And that's still equal to 49. So I think that s squared is going to be equal to 49 times 3 over 4, since I've got 4/3 s squared on the left. And then I'll take a square root of that thing. So this looks like 7 over 2 times the square root of 3. So 7 root 3 over 2. So that's where I'm coming up with that boundary. I just have to set them equal and go from there. Hi, a couple questions. Where did the 4/3 come from? That came from right here. If I add 1s squared to 1/3 s squared, that'll be 4 over 3s squared. Yeah, and then just, multiply the reciprocal to the other side to solve a fraction. Yeah, I suppose I did do that kind of fast. Told myself I wasn't going to skip steps, and well, oh well. Okay. Now that we've got the first question, hi. Mhm. Yes, exactly. So if I were to draw another arrow here, don't do that. Stop it. Don't jump me to the top of the, dang it. Undo, redo. Okay. So I am, taking this stuff and plugging it in right over here. Auto whispering again. Hey, there's another question. What's up?
Why just? That's fine.
Why just 0 for the lower bound on S? Yeah, solid question. So by convention, and in the way that you should probably be thinking about cylindrical and spherical coordinates when you're going to use them as a base for parameterization, is that our known parameters, being r and theta, and when we get to spherical, rho, theta, and phi, those all have some standard windows that we like to think about them in. So for theta, we always start with 0 to 2 pi because we're going to look at just one trip around the circle. We don't need to spin in multiple circles because we'll just keep retracing the same path. So our default assumption for the boundaries for theta are 0 to 2 pi. I'll come in and take some bits out if I think I need to. Right? If there's some language that says, like, only take the left half of this object, then I'd start, paring theta down. Half of an object might be just 0 to pi. Or if I want the negative half, pi to 2 pi might be the bounds I would take. But there's no language in here that says take, half of the cone. It just says we want to go all the way around. So 0 to 2 pi for theta. Similarly, r has a bound on it as well. We usually think of r as a positive number where we can. So if we're just going to stick r on a number line somewhere, not worry about it being a function, we'll restrict it to positive values. If I wanted negative values of r, which would just send me backwards through the origin, I would instead use an angle theta to swing around and talk about that point. So I use theta to pick up the negative back half instead of sending r backwards through the origin. Wow. So yeah, 0 will be our default assumption for our minimum radius value. Practically, a radius value of 0 just corresponds to the origin, and our cone has its tip right at the origin. So that's where we're going to start. Maybe you prefer that argument. Ooh, okay, we are into class time. Okay, so we got the cone done. Let's go do the sphere. And I'll just do the next one of these, parameterizing the sphere. The sphere. I bet you're not going to see this one coming. If I want to parameterize a sphere, I should think spherical coordinates. Think spherical. And in spherical coordinates, we have x equals rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. Or if I just spend a moment highlighting those differences, here are the main bits that I see. Right, so x and y are still going to be cosine theta and sine theta. That part won't change. But the radius value from polar coordinates takes on the value rho sine phi in spherical coordinates. But just remember, you have these transformation equations on your formula sheet. So if you need them, you can just go look at them. And in our particular case, we're going to use some stuff. Rho is 7. Phi is going to be S. And theta will be T. And then I just have to plug all that stuff in. So my parameterization of ST is the polar, or it's the equation looks kind of like this. 7 sine S cosine T = 7 sine S sine T sine S sine T, and then 7 cosine S. 7 cosine S. And once again, I'll need some bounds for my things, for my parameters. There we go. T still is going to be in 0 to 2 pi. It's still theta. I still want to go all the way around. And S, which is now supposed to replace phi, is going to start off as being between 0 and pi. Again, in spherical coordinates where we have our known parameters, we have a standard set of bounds that we want to use. For theta, again, one trip around the circle is just 0 to pi. But since phi, or maybe phi, depending on where you've heard it, just measures from the top of the z-axis to the bottom of the z-axis, only needs a half circle to talk about its full range of motion. So our default bounds for phi are 0 to pi. I said earlier, I'll just come through and make deletions from that as I think are needed. Because in this case, I think I need some deletions out of S, out of that phi variable. Because I want to, take the top of my sphere, just the top little bit up there, maybe the ice cream that sits in the ice cream cone, but then cut it off when it reaches the edge of the cone. So just like the previous example where we needed the intersection of those two pieces, I got to do the same thing right here. I got to go find the intersection of the sphere and the cone. This time, because I know I need to stop at the cone, I should be looking for an equation that's just phi equals some angle. Or in particular, S equals just some angle. So let's go and do that. I could just go back to the equation of the cone, which is z equals the square root of x squared plus y squared over 3, and then just start making some replacements here, which we know is going to be z equals 1 over root 3r. Just take a quick stop into cylindrical coordinates, x squared plus y squared, again being r, and then I can replace what I know right here. Z is going to be 7 cosine phi. 1 over root 3. R is 7 sine phi. Oops, sine phi. Blah. And I need to solve that equation for phi. So I am going to group my phi's on the right side of the equation. I'm going to multiply the root 3 over to the left side of the equation. So this is 7 sine phi divided by 7 cosine phi, which is just tangent phi. Hi there. Where did I get r equals 7 sine phi? Aha! That is my substitution for r in spherical coordinates. I believe it is even listed on the formula sheet. Maybe. No, it's not there. So I can get that by just taking r squared is x squared plus y squared and simplifying that equation, or it is a helpful enough substitution to use. I know we talked about it in class. But effectively, if you break down the rectangle the triangle that contains rho along your diagonal, z being your vertical distance, and then r is your horizontal distance. So just how we created that right triangle. Then r is the opposite side in that right triangle containing phi. So that's where I'm getting the 7 sine phi from. So they just say substitution for r. But then I've got phi, which is going to be the tangent inverse of the square root of 3. And say you totally forgot what tangent inverse of root 3 is, or the tangent value, the angle that gets you to a tangent value of root 3, you could just write that in. Or if you really remember your unit circle, you'll know that that's an angle of pi over 3. So really over here, this should be pi over 3. Okay. So, yeah, that's what I come up with. All right, let's take a look at another one. We are gonna move quickly. It's gonna be great. So, a chain rule problem. Say I've got some function, z is equal to sine of that times cosine of the other thing. X and y are both in terms of s and t. I want to find a thing. In particular, I'm after let's just solve for z partial s. Well, I'm gonna want to find the derivatives of z, the partials with respect to x and y. And then I'm going to want the derivatives of x and y with respect to s. So, zs, that's ultimately the thing that I want to find. Z partial s. It'll look like, for starters, that thing's x partial derivative. -2 cosine of -2x times cosine of 8y. And then a derivative with respect to y, the y partial. The derivative of cosine is negative signs. This will be -8 cosine of -2y. Sine. Nope, no more cosine. Yeah, sine of 2y. There we go. Sine of 8y. There we have it. That's our derivative. Then I'm also going to need the derivatives of x and y with respect to just s. So x partial s is going to be 2s. And then x partial or y partial s looks like -2t. Hi, question.
Why, for the, why, yeah, why,
Not. No, because I was thinking of something else. Yep. Yeah, that should definitely be assigned to x first. Looks like I also left the negative off. Yeah. I was focusing so much on the part I was taking a derivative of, I just kind of went into autopilot when I was writing down the part that didn't change. So in the end, when I want to write this thing out, it's just going to be 4 things multiplied in the correct order. There's an x partial right here times its derivative with respect to s plus a y partial right here and then its derivative with respect to s. So this is zx, this is zy, this is x partial s, this is y partial s. Then all we got to do is just write all that stuff in. In the interest of time, I'm going to leave that one as an exercise. We already wrote it all down, just put them into the right spots. If I've got time, I'll come back to that. I'm always out of time. Cool. Directional derivative. In case it's been a minute. We want to find the maximum rate of change of this function at the point 3, 0. Well, the maximum rate of change is always in the direction of the gradient. So let's go calculate a gradient. Gradient of f looks like an x partial of this thing, which will be negative e to the -3xy plus 3yx times e to the -3xy. All right, just do a quick product rule on my x partial. And then for the y derivative, I think this will just become a positive 3x squared e to the -3xy. So I've got my gradient as a function. Now I need my gradient at a point. So I need the gradient of f at 3, 0, which looks like this will be -1 plus 0, since e to the 0 is 1. And on the other side, 3 times 3 squared is 27. E to the 0 is 1. Which is -1, 27. And I am like basically done. I've got my gradient at my point. Now I just have to fill in the rest. The actual maximum rate of change is just the magnitude of that gradient vector. 0, which is the square root of 1 plus 27 squared. I would just leave it right there. And then u wants the unit vector in that direction, so that is going to be 1 over the square root of 1 plus 27 squared times negative 127. All right, so I'm in the direction of the gradient. I just want it to be the unit vector. All right, and that brings us into everybody's favorite problem, which is maximums and minimums. Oh boy. That later. So here we go. A maximum and minimum problem. Probably is the thing that'll take the most time on the exam. You can definitely expect to see one of these. And pardon me for just a second. Hopefully I got that far enough away from the microphone. Sorry to whoever's listening next. So, what do I want to say about one of these problems? First things first, we have looked at a couple of different ways to solve for maximums and minimums. This covers both the 14.7 closed interval method and Lagrange multipliers. When we get to the exam question, it'll simply say, find the maximum and minimum values of some function that satisfy whatever equation, being inside of some domain. Maybe it's a circle, maybe it's not a circle. You'll find out tomorrow. We will not be specific as to how. So if you want to use Lagrange multipliers, you absolutely can. It'll work on the problem that's on there. If you don't want to use Lagrange multipliers, you don't have to. You can use the closed interval method. Again, we're going to be non-specific as to the exact way that you need to come up with these things, so either method will work. We're not picky about a method. You know two different ones. Attack it however you want to. That said, I do want to highlight specifically that Lagrange multipliers is pretty much only for the boundaries of this thing. And that just generally holds true that Lagrange multipliers are good at finding critical points along the boundaries of regions, but they're not going to be as good at finding critical points on the inside of a region. So no matter which method we go with, step 1 is always the same. Set the gradient equal to 0. Gradient f equals 0, which really just means f partial x needs to be equal to 0 and f partial y needs to be equal to 0. So if I look at f partial x for my function, it looks like it's just 2x. Hey now, it's just 2x equals 0, so I get a critical value at x equals 0. I'll need to do the same thing over for partial y. And it's slightly more complex. 8y minus 16 is 0, which means that y is 2. Y is 2. So I get my first critical point at 0, 2. And probably this is the last one that we'll have time for, so let's just go through the whole thing. I'll lean over in a second and look at the rest of it. Part 2 is working on the boundary. And the boundary of that thing is going to be x squared plus y squared equals 36. Notice it's just equals right now. The full restriction is on the inside of this circle, but the boundary is just the part where we're equal to the edge of the function. So x squared plus y squared equals 36, and our function is x squared plus 4y squared minus 16y minus 2. That's our function. I need to rewrite f as a function of just a single variable. And a handy trick I'm going to use over here is rather than solving for x directly, I'm just going to substitute for x squared because I don't want to deal with a plus and minus. Really, because it's a circle, this is a pretty solid equation to try to use Lagrange multipliers on, but I've got that method worked out on the right, so I'll just talk about it in a second. I can do it without Lagrange multipliers. If I look over at my function, I see I've got x squared plus y squared and then minus a 16y, but I've only got a single x squared term. There is no linear x term over there, which is why I'm thinking solving the left for x squared is a really good substitution, because when I drop that in, my new boundary function value that depends only on y is going to be 36 minus y squared plus 4y squared minus 16y minus 2, and then I can take a derivative of that and get negative 6y. No, that's not right. This will be just 6y, there we go, minus 16 equals 0. Every single time we're doing maximum and minimum problems, we are taking derivatives and setting them equal to 0. It's just what we do here. So I take my derivative, I set it equal to 0, and I find that y is equal to 8 over 3. Once I know that y is 8 over 3, let's just leave that there for a second. Once I know that y is 8 over 3, I know that x squared is 36 minus 8 over 3 squared, which will get me to a couple of numbers. In particular, x is plus or minus the square root of all that jazz. On the exam, you'll get nicer looking numbers than this web work problem, so expect this to come out to a square number. For now, I just want to highlight some other key points, which are making sure to remember that we need the boundary values on this boundary curve. So I've drawn a little sketch here because I think that's the easiest way to understand it. But if I come back to my boundary equation, which is just x squared plus y squared equals 36, and I rewrote my function to be only dependent on y, that means I need to include bounds for y here in this step. I really should have said y needs to be bounded by something. It's got to be on the circle with a radius of 6. So it's got to be between negative 6 and 6. So then I'll bring that back over to the thing that is right here. I've got my 2 boundary points, along with the 2 critical points I found in the function itself. Let me just go highlight what those are. They came from 8/3 and whatever I got here for x. I also have my original critical point of 0, 2. So the last step is to simply plug everything in, which that part I did out ahead of time. Again, expect these numbers to come out nice on the exam itself. Because you won't have a calculator, so we put some effort into making sure that these numbers were like integer values. So when I'm plugging them in, you can see here in the first example, I'm just going back to the original function itself, plugging in for x, plugging in for y, and getting a number out the end. All right, and I know that I am out of time already because, of course, I am. So let me just talk about a couple of other parts quickly here. If you scroll over to the right in my notes, you'll see the Lagrange multiplier method, which I think worked out fairly nice for this problem. Again, because it's on a circle, Lagrange multipliers tend to work out fairly nice. There's also a diagram that shows more or less what we're doing here, slightly simplified version of it. But if you remember your quadratic surfaces, it can be helpful when you do maximums and minimums. The last problem that we didn't get to is the line integral problem. So in like 30 seconds, I just want to set this thing up because there's, I think, some value in that specifically. So what do I want to say right here? Figuring out the curve for this problem. And specifically, I want you to know how to figure out the curve for this problem right here. This one, I want to make sure that we know how to do this for the exam that is tomorrow. Right? So let's make sure we know how to do this one. Okay, so I want to be on the circle x squared plus y squared equals 16, going from 4, 0 to 0, 4. Straight line, please. Yeah, close enough. Another straight line, please. Again, close enough. The arc of my circle is going to be this. I am traveling counterclockwise, so I'm going this way. I have a starting value, which is here at 4, 0. I have an ending value, which is up here at 0, 4. I'm on a circle, so I think polar coordinates is a really good parameterization. So R of t probably is going to be 4 cosine t, 4 sine t. And my bounds for t, my bounds for theta are 0 to pi over 2. Because I'm going from the right side, the positive x-axis, up to the positive y-axis. If I were going to the left side, the negative x-axis, I would go 0 to pi. And if I went down the negative z-axis, or the negative x-axis, I'd be at 0 to 3 pi over 2. Right? Just remember what those 3 coordinate spots are. You set all that up, you do some other fancy things. Here's all of the rest of the work that will get you to an answer. I will fill in some details after class because again, I'm so out of time. So out of time. Okay. I think that's everything that I can squeeze into 5 minutes after class. So I'm gonna stop it right here. If you have other questions, I can probably take a few before the next class takes over. But other than that, good luck tomorrow. I believe in you. Okay, bye, 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 bye. Okay, just kidding. I have a little bit of time here, but with the next class not showing up to our classrooms, I'm just going to finish out the last couple of examples that I was hoping to get to. So, to add a little bit more detail up to this maximum minimum problem we were doing, we very briefly touched on it in class, but we needed to add the restriction that y over here. And actually, I liked it in red. Let's bring that back. Y needs to be in between its maximum and minimum values, which are negative 6 to 6. Now, because my boundary, or because my function on the boundary that I parameterized depended only on y, I only need to check the points 0, 6, and 0, negative 6, being those two that we see at the top of the circle over here. As this might be that they're preparing for the exam at the last minute, and maybe you're wondering, well, why didn't we need to check 6, 0, and negative 6, 0 being the left and right endpoints of this circle? Strictly, we don't need to check them because they cannot be the maximum or minimum because they weren't the boundary points of the circle as we parameterized it. If they needed to be checked, they would have shown up as critical points. And in fact, that's sort of where those 2 green points have been transformed to. If this were a perfectly symmetrical example, those would fall right at the x endpoint, so at 6, 0 and at negative 6, 0. But because the center of our paraboloid has been shifted up, those critical boundary points also shifted up. But say you're taking the exam and just wondering, you don't remember exactly which ones you should be checking, just check all 4. Worst case, you're just going to find 2 points that are not a maximum or a minimum, but that's not going to hurt you. So if you check all 4, you're just sort of safe that way. That'd be my brilliant advice to you right now, is to do it out that way. We didn't really spend much time looking at the Lagrange multiplier method, but for circles, Lagrange multipliers does work out pretty nice, which is why I had this one worked out for this particular problem. Again, you won't be restricted to a specific method on the exam itself, but it is worth checking out over here. The nice thing about the Lagrange multiplier method is that it just comes up with those boundary points without needing to go back and check them, right? X equals 0 ends up being a solution in our Lagrange multiplier method problem. So, not too bad right there. And then here was the line integral problem that I very, very briefly covered. So we also have two methods for calculating line integrals. Again, we'll be non-specific as to how on the exam, so you can work with it either way. This method was the parameterizing our curve, finding an r of t, getting a dr, which in this case is just finding dx and dy, and then looking at the dot product of those two things together. But I wanted to add in a little bit of extra detail for parameterizing this curve. In this particular example, we only have the first quadrant because we're going from 4, 0 to 0, 4, which is why t ended up being between 0 and pi over 2. But if we looked at just a few other paths that I want to write down over here, say I did 4, 0 to 4, 0 to negative 4, 0. Well, those are going to be the angles 0 and pi. If I were to say do 0, 4 to 0, negative 4, that's going to be angles of t that are in pi over 2 to 3 pi over 2. And just to round it all the way out, how about 4, 0 to 0, negative 4? That'll be t in the interval 0 to 3 pi over 2. All right, where I'm just looking at the angles that get me to each of those points based on polar coordinates. But the rest of what I was doing over here, my insides, this highlighted pink dot right here, this is really going to be what f dot dr looks like. Because in general, we can often express this as p dx plus q dy. If dr is just the vector dx dy, which is where this particular element's coming from, I can just plug that stuff right in. And then the rest of this was just some of the work that we did to actually calculate a value. Right? I actually go and integrate the thing. I left that mostly as an exercise, because hopefully that's just review from a previous calculus course. Now, the fun parts that we didn't manage to get to might not be in the spot where I thought I was. Oh, I am. Ah, right. So our last option here, the final thing that I didn't quite have a chance to talk about in class, was that we had two different methods for solving line integrals now, since we've hit both 16.2 and 16.3. So we can calculate our line integrals directly, or if we have a nice enough field, we can look at using the fundamental theorem for line integrals. Again, we'll be non-specific as to how. So if you can apply the fundamental theorem on the exam, you can calculate an integral that way. In our case, we need to look at p dy and q dx to check to see if our field is conservative. P being the x component and q being the y component. So I need to look at p partial y So derivative p, partial derivative of p with respect to y, it looks like it's going to be negative 2x e to the negative y. I also need q partial x, which looks to be negative 2x e to the negative y. And now I can see that those two bits are equal to each other. P dy and q dx ended up being equal, which means I have a conservative vector field, so I can apply the fundamental theorem for line integrals. Which means I just need to find that potential function. So I should integrate both p and q back up to find the original function. So the integral of p dx, notice I'm not going to be integrating py. I want to go back up to the original p, which was 2x e to the negative y dx. And I'll calculate an integral there. Do that in just a second, because I also need to look at the integral of q dy. And see what that was. This looks like 6, again, not qx. I want the original q, which was 6y minus x squared e to the negative y dy. All right, and now I'll have space to integrate these things. If I'm integrating the x part, this looks like it'll be x squared e to the negative y. If I'm going to integrate the q side, the y integral, the integral of 6y is 3y squared. And the integral of e to the negative y is going to be negative e to the negative y. So this thing comes back to positive x squared e to the negative y. And then check between those two integrals to put the function back together. I should really see that things that look similar on both sides end up being exactly the same. Because this thing is a conservative vector field, they must have come from the same original potential function, which in our case is 3y squared. Or let's write it out this way. It's going to be x squared e to the negative y plus 3y squared, where I can see that I have an x squared e to the negative y in both pieces. So it should make it into my potential function. But it should only show up once. I don't want it to show up twice because then I'd be off by an incorrect factor. I also see that there's this 3y squared term, but it only shows up in the y integral, which is what we'd expect. There's no x dependency in that term. So when I look at taking the partial x of my function f, that term should vanish. So that guy also ends up in the potential function. I can double check this by taking the gradient of the function real quick and showing that I get back to my original two field values, p and q. But now that I have f, the rest of the problem is very, very nice. The integral of f dot dr, the line integral along my curve C, which is whatever it might be. Keep in mind that this integral is just another form of f dot dr. It is just equal to f of b minus f of a. Where I'll just go figure out what my 2 points were. Highlight those guys right here. They are 1, 0, and 4, 1. I'm going from 1, 0 to 4, 1, so B is 4, 1. While A is 1, 0. Re-highlight these points again. Hopefully anybody that just goes back to look at the notes. And I can start plugging some things in. If I plug in 4, 1, I get 16 e to the negative 1 plus 3 minus Plugging in 1, 0, that'll be 1 times e to the 0, which is 1. I'll just write in 1 e to the 0 for now, minus 3 times 0, which is 0. And I would probably just leave my answer just like this. Or I could, I suppose, simplify the 1, call this 16 over e plus 2. But I don't really think that simplification is necessary. Again, you could just leave it in the line above. All right, and with that, I think I've now touched on all of the stuff that I wanted to get to in the review to really go over. If you're only going to focus on the least amount possible before this exam, so if you're looking to, optimize your review, I would look at all of the problems from here up, everything that's been covered in the video thus far. If you go to my notes, you will find there are a lot of other problems that I have worked out in here that just cover some big idea. I don't think that these are as necessary as the rest, so I'd mostly focus on the other things. But there are some additional problems if you're looking for more. Some other things that I thought were worth looking at. In this problem, I just really wanted to highlight from a broad perspective what we're doing with our maximums and minimums, because there are 7 different points on this problem that we needed to check. One critical point that lies on the interior, that's that green one right there. I have 3 different boundary curves, 2 diagonal lines and 1 vertical one. Each of those boundary lines has a critical point on it. So I parameterize my boundary, set it equal to 0, and solve for those critical points. That gets me those additional 3, the pink, the purple, and the blue one. And then finally, I have my boundary points themselves, the 8, 0, the 0, 7, and the 0, -7 that were suggested by the problem. Here's just another example of a Lagrange multiplier problem. Again, I think Lagrange multipliers work great on circles, but again, they'll only work on the boundary of a problem. So don't forget to check your interior points. Here is a second derivative test, just for classifying local minimums and maximums. Don't forget that if we're looking at the second derivative test, we need that value to be positive. The d value needs to be positive because both our second derivatives in x and in y must have the same sign. They're either both concave up or they're both concave down. The product of 2 negatives comes back to positive, which is why d itself is a positive number, but then we look at concavity being either up or down to decide if we have a maximum or a minimum. If we ask for work, know that that's just the line integral f dot dr. That's our formal definition of it. So if work comes up, there it is. This is a scalar integral, whereas we mostly looked at vector integrals in the 2 examples we did earlier. We looked at fields that were f dot dr, but the vector field version, there's also a scalar version for line integrals. This particular web work problem is just expanding on the idea of a conservative field check for 3 dimensions, or for all 3 parameters. I wouldn't expect all 3 to show up on the exam, but we could have just the 2 example, like we saw earlier. Again, focus mostly on the original problems that I went over, but also if we could find some potential function, which here we had a nice potential function, for calculating some integral that had all 3 variables in it. Again, works out very nice if I can find it. That potential function exists. Another example of a line integral. Here are just some of my thoughts on identifying fields. I kind of look around for some patterns within the vector field to try to match it up to a function. Most of that section, most of the 16.1 vector field section is meant to be an aid in solving line integrals, so don't expect much to be asked about fields directly. Expect them to come up in the subject of line integrals. Here was a parametric tangent plane, if you want to look at that. And finally, one example looking at level curves and the domain and the range. Keep in mind that if I'm finding the domain of a function, in particular, I'm looking for the domain of a log function here, I just want to set the inside of that log greater than 0, because I'm not allowed to take the log of a negative number. Okay, and I'm calling it here because I'm pretty sure my laptop's about to die. Okay, bye, 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 bye.